Okay, hello everyone. It is my pleasure to welcome and introduce our speaker today, Farbod Hassani from the University of Oslo. Farbod got his PhD from the University of Geneva, working under the supervision of Martin Kuntz. After that, he went for a postdoc at the University of Oslo, during which he also had some extended visiting periods in Canada, at Perimeter, at McGill, and also in South Africa, Western Cape and Cape Town universities. And then recently he got a grant from the Norwegian Research Council to start a 4-year project still at the University of Oslo. Farbod is an expert on modified gravity and dark energy models and simulations of these cosmologies using relativistic codes, and he will tell us about this new project that is starting now, NEVO, illuminating the dark cosmos.
Thank you, Marco. Thanks a lot for having me. I prepared my talk to be relatively introductory. I apologize for the experts if it's not too technical. So this is basically the title of my talk and the title that I applied for a year ago in the Research Council of Norway, which I'm going to work on during the next few years. These are my internal collaborators, David Multan, Hans Smith at the University of Oslo, and the external collaborators here. You're always welcome to visit University of Oslo, the Institute of Theoretical Astrophysics here, but we have a lot of beautiful sceneries. Just remember, you might not want to come in winter because the weather is really harsh, but the upside is that you can have auroras. So you're welcome to visit us if you plan to. All right, let me start with this introductory picture of different scales in the universe. So on top left is Earth, and from left to right, we basically zoom out to reach out different scales in the universe. So we go to solar system, we go to galaxy. This is going to explain what kind of objects I'm interested in my research. So when you continue zooming out, eventually you reach a relatively boring universe, which is called observable universe. And by relatively boring, it means that no matter where you sit in or what direction you face at, you see basically the same kind of structures. Or equivalently, we have almost homogeneous and isotropic universe. To be more specific, part of my work is about embodied simulations. So in my embodied simulations, or what people do in cosmology, we have like boxes of the scale of order 1,000 megaparsec, which if you're familiar with light year or kilometer, these are the numbers. And since we have very large scales, we encounter with very large masses. So the masses we have, depending on resolution, but it's usually like around 10 to the 12 solar masses. Although the universe seems boring at very large scales, we have isotropic and homogeneity, where we can answer to many interesting questions. For example, what are the main components of the universe? How do the cosmic structures evolve and arise? We can discuss the initial conditions and also the fate of our universe. Okay, so an interesting observation. Around 25 years ago, I used to say 20 years ago, and now 5 years passed. So around 25 years ago, cosmologists observed that our universe has a late time accelerating expansion. So this observation has made from the distant supernovae observations, and supernovae are important because they are very luminous. So what we observed is that by plotting the magnitude versus redshift, we saw that they fit better to a universe where we have 70% dark energy budget, rather than being completely dominated by matter. And as you can see, if you have a universe in the dash line with only matter, it makes the universe decelerating. So we know that if we have expansion, but it should be decelerating if you have only matter, but it's accelerating. So it puzzled us. And later on, from the cosmic microwave background observations and large-scale structure observation, we confirmed the same thing. So we know that what we know today is that we have a sort of exotic energy called dark energy, which makes up around 70% of the universe budget. The two important features is that it has to act opposite to gravity and doesn't seem to cluster very strong compared to matter. So intuitively, if you consider like Boltzmann's equation, for example, it might seem difficult to model anti-gravity behavior, because whatever density you put on the right-hand side, you basically get potential wells, and potential wells tend to make attractive forces. For example, if you have galaxies, you make potential wells, and this makes things come closer to these objects. So if you want to have something which makes repulsive forces or cosmic acceleration at large scales, intuitively we can think of a global trough in the universe where distant galaxies are receding from each other. And theoretically appears to be that just adding a constant in the Poisson's equation does the job, where you get such a behavior. So we have local gravity behavior, we have potential wells, but at large distances, we have these repulsive forces, which makes the cosmic acceleration. Of course, this is a practical theory. In GR, we have to add it in covariant form, so we have something like this. You can stop here and say, okay, I'm happy, I found a constant, new constant in nature, which works relatively well with observations. But you have to remember that this constant is not motivated by our theoretical models. So the constant that we predict from theory is way different than the one that we get from observations. So one can naturally think that, okay, instead of a constant, we can consider an exotic form of matter or dark energy or energy that appears to be a scalar field. And this scalar field doesn't vary much with space. So it's very close to what a cosmological constant we can have. And people call this dark energy. But in principle, rather than just a scalar field appearing in this form, people have considered a lot of different possibilities. So usually the distinguish they make is that if you change the left-hand side of the Einstein's equation, we call it modified gravity, and if you change the right-hand side, we call it dark energy. But these are not really meaningful differences. So I use modified gravity and dark energy interchangeably in my talk, so they were basically the same thing. And also note that the so we so far I was discussing the equations, but the most fundamental elements are actually actions, because actions you basically write the equations in a simple form, and you can apply some simple rules to derive the equations of motion for matter and gravity part, as well as the scalar field part. And also we can study symmetry, so this is more interesting to me. So the Einstein-Hilbert action, you have the Ricci scalar and matter part appears. If you add a cosmological constant, it just being appearing as a constant in the action. But you can think of a general theory which you can have coupling between Ricci scalar and the scalar field. So you can think of a new theory. You have a new scalar field, and the scalar field evolution. I mean, you can have a function of the scalar field. It's first derivatives and second derivatives. I don't go beyond second derivatives, but in principle, you can also go that. So let's think about this action. And what the question we have is, what does the universe look like if I consider a new dark energy? So to answer that, I need to first find the equations. So I need to vary the action with respect to metric components. I get the modified Einstein's equations. I need to solve to find the scalar field evolution. I need to vary with respect to scalar field. And then when I do that, I need to specify the functions. So people have considered different possibilities. For example, one possibility would be the quintessence action, which you have kinetic term minus potential. Or you can think of K essence, which is a general function of the scalar field and its first derivative, and so on, kinetic gravity grading, F01, etc. But one thing that is important is that still these functions don't tell us what does the universe look like. We need to be more specific. We need to parameterize these functions specifically, and for given parameters, say, okay, this is the evolution of the universe, and then we can compare with observations. Okay, as we can see, for example, I considered one kind of parameterization, but you can think of any other. So nobody has told us that this is the best parameterization. What people usually do, okay, we go with this parameterization and we constrain the data with constraining X data. But as you can see, you can think of infinite amount of parameterization, right? So it's a very difficult approach. And the question is, can we do better? Can we avoid this kind of parameterization and only rely on some variables that really are important for us? And the answer is yes. Fortunately, we can do approximations. So the first approximation is we assume that the gravitational potentials and metric perturbations are small, which is valid in cosmology. I mean, it means that we don't want to study black holes in our simulations or in cosmological scales. The second assumption is that the scale-effect perturbations remain small. This is also a valid assumption based on observations. Observations show us we don't have a very huge amount of clustering for dark energy. And you can show that within these limits, you can specify these covariance theories with only some limited number of effective parameters. For example, for the K essence, we can show that with these approximations up to a certain order of perturbation, you can only study the evolution of speed of sound squared and the equation of state. So these are the two relevant parameters. No matter what theory you consider here, you can effectively effectively approximate it with these two functions at the relevance. And then we can use observations to constrain these parameters. Of course, with this approach, you basically neglect the underlying theory because you cannot easily recover from the effectivity theory, going from effectivity theory to fundamental theory, but it's a more relevant approach for observations. And if you think about it, it's actually what we usually do in physics. For example, imagine somebody asks you, I have molecules in this room. I want to know the state, the position and velocity of molecules in the next time. So one approach would be to compute the precise position of all molecules and their interactions and do it by hand or by computer and see what's going to be next. And you don't know what you're going to do with that even. But the other approach, which is the effectivity approach, tells us we rely on some parameters which actually are important in this case that we are interested in. So we rather express this gas with pressure, volume, temperature, and entropy. A less familiar example would be car traffics. Car traffics can be modeled as a fluid. So one can study all the details of these cars and their sizes and how they interact, like the drivers interact. But to study as a large scale, you can consider just two parameters, the density of the cars and the velocity. And we can see a lot of interesting phenomena happening in this kind of modeling. So this is the idea of effectivity theory. Instead of parameterizing at the covariance level, you just approximate and study some effective parameters. And then you use observations to constrain these parameters. So these are two features. So it's very convenient because we can have a general action for class of theories using the effectivity theory of dark energy. And one can show that it's actually the minimal number of parameters that you can have for the observation of predictions. So now it brings me to the first stage of the NEVO project. I don't have time. You can check quickly just how fast I have to. Okay, I have to be very fast because I prepared my time for 4 to 5 minutes, sorry. So the first stage would be the linear study of the project. It means that you basically use this action and you derive the equations of motion which are. I mean, you first do symbolic calculus in mathematics where you derive the effectivity theory parameters and then implement in high class code and see how does the universe look like at larger scales. So this is the idea, and then we can constrain the current data to constrain these effectivity theory parameters. The second stage is the nonlinear implementation. We basically derive the nonlinear equations for dark energy. I will show you why it is important. And then we implement in an embodied code, and we see how precisely the universe looks like. I mean, precisely, it's some shaky precisely. So let me skip this one, the relativistic treatment we can have. just to mention briefly that we solved 6 degrees of freedom in a relativistic treatment, and we solved the full Einstein's equations, and we also solved the geodesy equation, which is important for dark energy implementation somehow. All right, so as an example, if you have a K-essence clustering, so this is from a code K-evolution, which I developed during my PhD, where you can have non-linear K-essence. So on the left, we have the K-essence density. On the right, we have matter density. At redshift 6 is very early time in the universe evolution. And when we continue evolving, basically the matter structures form, and around it, we have also dark energy structures. You might say, okay, it might not be that important, but in principle, they can have distinct effect in observation. So if you want to really probe K-essence, we need to include all the details, including uncertainties. So the idea is that we are the God in embodied simulations. We start from some initial conditions, which are homogeneous and isotropic. We put the ingredients. Here I have cosmological constant. Here I have K-essence, and then I evolve the universe. You see the time top, and then you have 2 different universes. The question is which one is closer to what we observe. Of course, what we observe is not that we don't have full access to this snapshot. Instead, we have only access to our light cone, and these are the limitations we have, and we can explain. So the third stage would be to identify smoking gun signatures of dark energy. So we need to really probe what kind of signatures these dark energy models can have, and try to rule out or confirm them. So the first thing one can do is just simply by computing the correlation function of dark matter distribution. So these are dark matter snapshots. One can just plot the power spectra and see. And so in the bottom, we have the ratio of the dark energy model with respect to lambda. So these are one distinct signatures that these models can have. The next closer to observations is that let's find the halos. Halos are gravitationally bound objects. We find them, and then we compute the 2-point correlation function. Surprisingly, when you do it blindly, you see no signal. So you get something large when you do for matter power spectrum, but for halo power spectrum, you see no signal. And we studied that, and it appears that when you have 2 different simulations with dark energy models, the halos have different biases. So bias is an important parameter. If you need to get the signal correctly, you need to select halo samples with the same bias within 2 universes or within 2 simulations. Right, let me be fast. So the light that propagates in homogeneous universe is getting deflected and redshifted due to numerous effects. So these are just the equations you simply get if you solve a geodesy equation in a homogeneous universe around FLRW background. So we have weak gravitational lensing and ISW with Sciama effect, for example. Let me skip the weak gravitational lensing. So in ISW, you cannot see the title here. So in the integrated Sachs-Wolf effect, how's it working? Okay. Right. So it happens when we have decaying potential well. If you have a fixed potential well, the light, which is red, goes into the potential well, it gains energy, becomes blue, and climbs out the same amount of energy level and becomes red again. While if you have the decaying potential well, it gains a lot of energy, but it loses less energy because it has to climb out a shallow potential. So the photons are blue shifted in this kind of universe, and that happens when we have dark energy because the potential is decaying. In simulations, we can make such maps, and these maps, each point shows the photon has come from a certain direction, whether it's blue shifted or red shifted. And you can see it's mainly blue shifted because of decaying potential, but it also happens that they are red shifted because of nonlinearities. Some potential wells grow. And in principle, we can use these kind of signals to compare the models and constrain them. One interesting aspect of, especially because we are using relativistic embodied codes, some dark energy models can have gravitational wave signatures. For example, this is a symmetron model that has phase transition, happens at late time in the universe. On the right, we have the scalar field. On the left, we have the gravitational wave strength. You can see what we are plotting exactly. This is Hij dot, Hij dot. So this scalar field basically can have to minimize the Mexican hat potential. It can be either in the positive or negative minima, and we can have domain walls. So you see that when domain walls collapse or collide, there will be some gravitational wave signatures. And the sound, if I can get it, is actually from the power spectral gravitational wave, but shifted to the frequency that we can hear. So basically, when these domain walls collapse, there will be gravitational wave that is a background gravitational wave that freely propagates through the universe, and in principle can be used to constrain such theories. Okay, so this is the last part of my talk. Let me tell you a bit about the importance of including nonlinearities in dark energy models, which is usually neglected in literature because people, think that the dark energy perturbation is small, because their nonlinearities cannot become large, so we can neglect them. The first thing is that nonlinearities can have non-negligible effects, especially given that we are going to very high precision data. Okay. And the second thing, which is way more interesting, is that we might find some nonlinear instabilities in these kind of models. So I'm going to show you two different scenarios. So this is the k-essence, the speed of sound squared, shows how fast the perturbations propagate in this kind of fluid, in the fluid approach. And for large speed of sound, I will show you that everything is fine. The universe is fine. We have some small nonlinearities due to dark energy clustering. But I'm going to show you for a small speed of sound, what happens is that we get a blow-up in the dark energy field. So I can just show you very quickly. So this is a simulation showing that on the right, we have matter density. On the left, we have k-essence density. And what happens is we get some nonlinear structures up to redshift 0 from this dark energy. And you see that the structures are very large. It's like way larger than the real radius of the halos. However, if you consider small speed of sound, and if you solve for the scalar field evolution, this is the 2D plane of a scalar field, and the red color shows whether it's below the average, and the blue shows whether it's larger than the average. And if you solve this equation, everything is fine, but suddenly blows up. So we were wondering about this question for a long time. We didn't know if it's a mistake from us or if it's a numerical instability or what. So we have this equation. Basically, this is the equation that we see the blow-up happens inside. So we identified that this term is a problematic term. What we did, we gave this, we said that let's make it very simple in 1D, and we gave it to some mathematicians, like in our institute. And still they are working on it. After 6 years, they haven't solved it. So what's in the first paper, which I was also part of, it was very difficult to.
Sorry, what is the issue? What is the most dramatic one?
So these kind of equations, when you have wave equation, sorry, this is wrong. This is, oh no, that's true. So this is the wave equation, which is fine. But when you add this type of nonlinearities on top of wave equation, they can show that no matter what's the speed of sound, what's this coefficient, this alpha, it blows up. So that's something they were dealing with. So the only thing we saw in simulation is this type of blob. We saw that the scale of it develops becomes sharper and sharper at some point blows up. And this is what they have showed, they proved, well studied. It's a long paper with a lot of proof of existence, like scaling relation, and a lot of things that I really don't want to go into the details, and it's very difficult for me. But they also have shown that there is another type of instability which we've never seen in simulations, is that for finite speed of sound, this beta, I remind you that is the speed of, basically, it's the speed of sound squared. Alpha is the coefficient of the nonlinearity. And there is another type of blob, which we call it M-type blob. And it's very similar to blob happens in Berger's equation. So you have a wave that is propagating, but there will be another wave coming from this part, and there will be a point where its gradient becomes infinity. This has been studied, but they cannot prove. So it's a conjecture that you get this kind of blob, and you get it for no matter beta is. So even for superluminal speed of sound, which is non-physical to us, they prove it that you should get that. But the proof is not very robust in their perspective. It's good enough for me. Okay, so the final stage of this project would be, so we have some machinery, some codes, and some results. We need to find constraint on these effective theory parameters, and at the end of the day say, okay, hopefully rule out cosmological constants and say that this is our dark energy. But this is very ambitious, you know. And to do that, we need to utilize emulators, because running embodied simulations are very expensive. We need to apply for computational resources. It's very costly. But instead, we need to use embodied simulations to develop some machines, like machinery, that for a given parameter tells us how does the behavior should look like. So these emulators, we have done one project on, and at the end of the day, these emulators should be used to constrain parameters. All right, this is the summary of my talk. I just explained, I hope I convinced you that we have a late time accelerating expansion in the last few billion years of the evolution of the universe, which is caused by dark energy. In order to understand the nature of dark energy, we need really thorough investigation of possible candidates. We don't need to rely on one candidate. We need to really explore all the possibilities and see their impacts on different stages of the universe. How does the universe look like actually for each candidate? So in fact, the consistent and accurate modeling of these candidates have been largely neglected because of numerous reasons. Like neglecting nonlinearities, because it's hard to get the equations of dark energy. For example, you need symbolic calculations. It's also hard to study in simulations. And also, people have usually focused on non-observable quantities, like power spectra. But we need to construct observables, like under light cones or other small-scale observables. And also some inconsistent use of Newtonian embodied codes to study some dark energy candidates that should be treated with relativistic codes. And all these, in these projects, we try to utilize relativistic embodied codes along with high class, which is a Boltzmann code, to accurately model these candidates and hopefully find the best constraints on the parameters. Thank you.
Questions? So do you have any constraint at the moment on sound speed or any parameters of your?
Yeah, that's a good question. I mean, there are some loose constraints from the even CMP data of C, but that's not really what because in principle, I mean, first of all, CS squared can be time dependent. I usually consider it as constant. But what I haven't done any constants with, so I haven't worked with data to get any constraints. But the constraints that I saw in the literature is that the speed of sound should be large. So this is what loosely people have constraints.
But from landscape structure or cosmic shear, you cannot get any.
I haven't seen. Maybe there are some, but usually it's relying on the linear implementation of these models. If you go beyond linear, the constraints will change. This is something that we have discussed in the papers. For example, the ratio of power spectrum will change if you get to
Something like that. It's about the light cones. What are the limitations you have in building of light cones in terms of volume, in terms of computation?
In terms of compute, we have to store. We don't do it. We store light cones on the fly, but we study the data as a post-processing. So it's like, yeah. But the expenses would be, if you want so many light cones, you have to have large storage space, because these cost a lot. So usually what we do is one full skylight phone and several light phones we save. We need to study of these quantities. But otherwise, I don't think they really slow down simulations. Maybe a bit.
Laura.
Can you give us some details about the embodiment that you have? So, in terms of size, number of organization, and things like that. So there are not variants inside.
There are no variants, no. So there are several downsides that I mentioned. It's a fixed grid, so we don't have zooming, contrary to Newtonian simulations, they are very accurate at small scales. These are not accurate at small scales at all. So, and by nonlinearity, I meant like.
What is the special solution?
So the one I consider, we can go to 0.1 megaparsec, not below that. At least this is what I think. And what else? But this is mainly because it's relativistic. We consider it for large scale simulations. The box sizes we consider as like 4 gigabytes of the range.
The difference that I saw in terms of bias were at very, very low scale. So they are not affected by the resolution of the simulation.
No, we don't think so. At least, that's a good question. In the matter power spectrum, so we can trust, I mean, if we take into account, for the matter part, we can trust up to k+1. But for the ratio, we can trust to higher rate numbers. But for the halo, we haven't really studied the convergence test. That's a good question. But we don't think that's the problem, because the thing is here, we have nonlinear bias fixing. So if you don't have nonlinear bias, then the signal would be completely different compared to matter. If you have a different bias for these select samples, then the signals wouldn't be the same. I don't know if I'm clear. So the idea is that if you fix mass, like if you consider mass cut, the signal doesn't exist. And this happens for massive neutrinos as well. We didn't only we did it for dark energy. But when you consider halo selections with fixed bias, up to at large scale, which is the linear bias indicates, they have to have the signal recovered. But at nonlinear scales, they have a different rule. But I agree, maybe the resolution tests show us that you cannot trust beyond 0.7, especially because these are halos that are matter.
That halos defined with one of friends.
We use rock stars in the phase space.
I have a couple of quick ones. So one is the difference between lambda CDM and K essence is getting larger at low redshift, or is there any sweet spot, I don't know, at intermediate redshift if you have to look for differences in the two?
Only at it gets higher at lower redshift.
Okay.
There is no because this is constant W.
Okay.
If we have WA, that can change things.
And the other one, you show the gravitational waves. So this is a mechanism to emit gravitational waves at very low redshift, right? Because I think the redshift was going towards 0, and in your simulation towards the end, there was this domain collapsing. Yes. So that's a sourcing of gravitational waves in the very local universe.
Yes.
But on very large scale, because your scale here is it co-moving physical? Redshift 0, this is still 100 megaparsec. Yeah,
this is very large scale. But what we did, you're completely right. So this cannot be within the frequency range that nanograph, for example, can take.
Mm-hmm.
What we did, we studied if we extrapolated the parameters so that if we have it in the range of nanograph, for example, what kind of signature it brings. Because the signature, for example, the quantum wavelength of this model basically tells us where is the peak of this gravitational power spectrum.
And where is that? 100 megaparsecs?
No, it's 1 megaparsec.
Well, okay. And can you get to something fairly isotropic, or you expect some anisotropy in that?
Isotropic in what?
Like the gravitational wave background is fairly isotropic, except okay, today they reported a possible anisotropy, but it's fairly isotropic. So in that case, if the source is very local, can you still get something isotropic?
Yeah, it is. The signal that we see is isotropic with some peaks. It's not very distinct. I haven't put the plot here.
Okay. Any other question from the room? Yes.
You want the previous slide? Yes. So this scale tells you that the pressure difference of 10 to the 6.
So this is, I mean, this is not really meaningful math, because just to show that we get difference between lambda CDM. This is difference between KSNs and lambda CDM. So this map is for lambda CDM, we get a similar one for KSNs, and we subtract. It's not really meaningful because we have to really compare the statistics rather than the point one. So what you say, why you get, it's like 10 to the minus 6. Right?
10 to the minus 6.
Yeah, when it's multiplied by 10 to the 6, you get this number.
Yes. I have another curiosity. If you go back to your relativistic treatment, what are the most important effects in the case of KSNs? Just what is the one affecting more the results? So between the Shapiro debate, the things.
Very good question, because I mean the most sensitive is this one. I think I have it now. The most sensitive is ISW with JAMA, is like 33% difference you get from KSNs compared to lambda CDM. And Doppler is like 5%. Shapiro time delay is not large. It's basically the difference between the potentials from the source and the observer. That's small. It's like 2%. So with gravitational lensing and ISW with JAMA, which I discussed, are the most important ones for this model.
Okay, if there are no more questions, it's it for
For the whole group.